Hey, how are you guys? So I'm going to be doing in this video a requested thing. Somebody asked me a while ago to do Stewart's theorem, a proof, and how it's used. I'm going to get to that in a moment. First, I want to make a quick announcement about two things. Number one, September 25th of this year, 2021, if it's not this year when you're watching this. The AMC, it's an online math contest. It has teams, it has individual rounds with team rounds. There's going to be a link in the description. It looks very well organized at this point. The team behind it, from what I can tell, really brilliant people, and they're just working to give you something that will help you. And so you want to check that out. It'll be on my description and on my website on the calendar when I have a chance to update that as well. The next thing is the AMC 1012A is going to be held November 10th, 2021. This is for the 2021-2022 school year. If you haven't heard yet, yes, it's 100% confirmed. The test for now will be in November. That is 8 weeks and 5 days away. That's not a lot of time. I hope that you are preparing. And with that, let's get to Stewart's theorem. And now for the proof of Stewart's theorem. So to get started, we need to know one word. It's called a Cevian. And a Cevian is named after, well, of course, an old dead mathematician. Giovanni Ceva from Italy came up with this sometime long ago before our time. And as such, he now gets things named after him. Being really good at math is a good way, better than me, way better than me, is a really good way to get things named after you in the world of math. Or you can be creative and come up with something like the Wooga-Looga theorem, which I will leave you to investigate on your own. Anyhow, so Cevians, let's get started. You're going to need a triangle. Webster's dictionary says there's also a Cevian for tetrahedrons, I think, but I don't know if that's accurate because I haven't investigated it yet. I assume Webster's dictionary is not going to get that wrong. Merriam-Webster online. You're just going to take a random triangle, and what we're going to do is we're going to label it capital A, capital B, capital C. And you're going to need a random line from the vertex of one side to the other side. It can be anything. It could be an angle bisector. It could be an altitude. It could be none of those things. It could just be like this, some kind of random line. Okay? That line is called the Cevian. That's the Cevian. Okay, so then if I call this D, okay, and I call this point D, the little lowercase d is the length of that segment. Going this way, this will be lowercase a, because you're coming from capital A, and opposite over here, this is common notation, lowercase b is opposite big capital B for the vertex, and then you'll have little c here. Now, my first question is, what if we attached, if this is little c, then what if I attached a ZERS to that? It'd be Little Caesars. Okay, so any case, that's just terrible, terrible humor. Not even, don't laugh. That's bad. Okay, so now, what are we going to work with? We're going to actually try to prove something from this. I'm going to call this theta. Why theta? Because, again, some great people gave it to us, and we use this for angles a lot. It's just like x, but we use it for angles. Other things get used for angles too, like alpha, beta, gamma, various other things. But for now, theta is the easiest one to use. Now, keep in mind that this angle over here will be 180 minus theta. And what we're going to use, by the way, this is not my proof for Stewart's theorem. I mean, it's been proven by so many different people. You can find it on AOPS as well. I'm just going to demonstrate it to you. So we're going to do law of cosines. And law of cosines is very important. You should know it. It's not required knowledge on the AMC 10, but sure, it can help you. And it is for the AMC 12. And it might be required knowledge for the AMC 10 in the future. So what are we going to do? We're going to do law of cosines using this angle right here. And I'm going to say theta, right? Opposite it is this little c. And you're going to write c squared. And the next thing is, I like to think of it, I use little mnemonic devices. Again, mnemonic, M-N-E-M-O-N-I-C. It means a device for memory. And there's another one for Stewart's theorem we'll get to as we develop it. But for me, I like to think of it, it's like Pythagorean. Meaning that I'm going to take the other two sides, I'm going to call this one m and this one n, and I'm going to take those and I'm going to square them and set them equal to this, d squared plus m squared. and then it's going to be minus 2. There's always a 2, don't forget the 2, and you're going to take one of each of these. This is why you don't want to memorize letters. Memorize where they're located and how they interact. So like Pythagorean, this is the opposite side from whatever angle you're working with. The other two sides get summed and squared. You're going to minus 2 times, and it's going to be a copy of each of these but not squared. So we're saying 2md cosine of theta. This is all one term. It's all being multiplied, okay? If we do the same thing with this angle over here, this is law of cosines, okay? You're going to have the opposite side to it is b. So you're going to start with that. B squared equals, take the other two sides. D squared plus n squared minus 2nd cosine of 180 minus theta. Okay, great. Now what? Well, there's a cool trig identity, and I'm not going to break it down for you now because that's not the purpose of this video. But you should know that cosine of 180 minus theta is equal to negative cosine of theta. And why would we want to do that? Because it lets us do cool things. And so we're going to put negative cos of theta here in place of this expression, negative cosine of theta. And this part can be canceled out. Now, I'm going to go ahead and move this negative to here and rewrite it. Actually, I'm just going to solve it for cos of theta, if you don't mind. So I'm going to get b squared minus d squared minus n squared. This negative and this negative combine to make positive. So we can kind of get rid of that. And we're going to divide by 2nd. And why is 2nd not so great? Well, because it's second and you'd rather have first. Anyhow, that was also a terrible joke. You'll get those a lot around here. I hope you don't mind. This is cosine of theta. Okay? Now, let's do that with this one up here as well. We're going to get c squared minus d squared minus m squared. This time I'm going to divide by negative 2md, and that's also equal to cosine of theta. Now, those are both cos of theta, which means they're equal. And we're just going to set them equal with the other two expressions. So we're going to get, let's see, let's do the, I think I want to do the c squared. I think I want to do the c squared. We'll find out. C squared, no. Okay, yeah. Let's do it the other way. So b squared minus d squared minus n squared. I don't know if I'm doing the right way or not here. We'll see. It'll all work out in the end. Over 2nd is going to equal c squared minus d squared minus m squared, all over negative 2md. Okay, now you might think, oh, I should put that up there. Who cares? Just, move it over here. So we're going to now cross multiply. Why cross multiply? First, get rid of the 2's. Why do we want 2's on both sides? Just multiply by 2. It disappears. We can also multiply by d. Let's do that as well. Okay, great. Now that that's done, there's a negative m here. You're going to cross multiply. In general, when fraction equals fraction, you will cross multiply. Sometimes there's faster ways, but just in general, okay? So don't think too long about it. You're just going to go over to here and multiply. You're going to get negative b squared m plus, because the negative times the negative is positive, md squared plus mn squared equals, this n is now transferred up to here. You're going to get c squared n, and then minus d squared n, and then minus m squared n. Okay, so I'd like to get things to where they're not negative. In general, I just don't like negativity at all, really. And so I'm going to avoid it at most costs, which means I'm going to move these over here. Why do I hate negativity? Well, for many reasons. Obviously, yeah, negativity in general in life, it's not good, it stresses you out. But furthermore, when I was young, I would make mistakes with negative signs all the time. So I just avoid them whenever possible. Sometimes you can avoid them though. So we're going to move these over here, and we're going to get, let's see, I think I want to do m squared n. I'm going to put this one next, plus mn squared, and then the dn squared is going to move over. So I've used this term and this term now. The dn squared is plus d squared n. I'm going to be moving, I Actually, we're going to put the plus md squared as well, so plus d squared m. And then we're going to move to the other side. We're keeping c squared n over here. And actually, I will put the b squared m first. It was negative. It's going to become positive b squared m plus c squared n. Now, what can we do? Well, you might see here that this can factor out a copy of mn. And what's left is m plus n. And then you have plus d squared. And I can also make that m plus n. And over here, we'll write b squared m plus c squared n. Okay, now what? Well, now it all comes together. If you look up at the diagram, m plus n is in fact the same as a. Again, lowercase letter opposite the capital letter is the side opposite the capital letter. That's not always, it's just conventional, okay? So then you're going to put the a in here, but I'm going to rearrange it. I'm going to write it right here. It's going to be mna. And I'm going to put MAN. And then here, this is an A, and this is D squared, and I'm going to surround the A by two D's. And then we're going to move over here, and I'm going to split the B on either side of the M. And everything is positive now, which is great, and it looks like this. This is one of the ways that you can represent Stewart's theorem. And the reason I've represented it this way comes right back to this. It's a mnemonic device, and it's kind of weird. I hope nobody gets kind of offended by it. It's just something to say. I don't know why a man and his dad would do this. Don't think about that. Just think about easy ways to memorize things that you can quickly draw up from your memory on the test. And the common phrase used to memorize this statement is a man and his dad put a bomb in the sink. It is what it is, right? It just works, okay? I wouldn't recommend saying that in an airport at all, ever. For reasons that you can discover on your own by researching. So how does this work? What I want to do, don't just memorize the words too, because when you get one in a real life situation, a problem that you're trying to solve under time pressure, it's probably not labeled A, B, C, M, N, all those things. So I like to memorize a visual thing, kind of like over here. It's like Pythagorean minus two copies of these, not squared, and then cosine of the angle that's opposite this side. Kind of like that interplay. I like to visually see things. So let's see what it would look like visually. We're going to get the two pieces of the side the CVN connects to times their sum, right? That's the man part, okay? The DAD part is the CVN itself times the entire side times the CVN again. There's man plus dad. When you do the BMB part, I like to visualize it as crossing over the CVN. So I take the B value, I go over to the M value, and I cross back over to the B value. You have to cross over the CVN for it to work. That way, if I give you a different triangle, and I call this X, and this is V, and this is W, and this is L, and this is M, you know it's W, L, W, and V, M, V, right? You're just crossing over the CVN to get to the other part. That's how you want to think of it. Again, it's C, cross over to the side opposite and come right back to C. It's both plus signs. Memorize the visualization, not necessarily the words. The words help, but you're going to have to memorize the visualization of how it's put together. That visualization is actually faster than this. Okay, so how do we use Stewart's theorem? Well, that's a great question. There's not always an opportunity to do so. But if it comes up, it can be a super quick way to take something down. Granted, in most questions that you can do Stewart's theorem, there's often other ways that you can do them as well. Off the top of my head, I can't think of one that requires it. Maybe there's one or two, but I just can't think of that right now while I'm filming. And so let's get to one example. It was actually from the 2021 AMC 10 and 12. It appeared on both tests. And I'm just going to cut to the video that I already filmed of it. I'm not going to refilm it. I'm going to link it to here. But what you should understand is a lot of times the test makers, this is just kind of my hunch, they seem like they like a certain theme for 2 to 3 years or 2 to 3 groups of tests in a row, since we're in the same year as the spring tests or the late January, early February tests. And so you should probably have this down pat, ready to go in your small notebook, and reviewing it the day of the test and the week before the test and the week before that, so that you can constantly reinforce this idea. just in the event that it does appear for a second time in a row. Now, there's no guarantee that's going to happen. It's just something I've noticed that they seem to sometimes do. Like if similar triangles is in one, it will show up again. And there's like a 2 to 3 year period where common concepts from the previous tests appear on the next one, which kind of makes sense. I mean, there's kind of thematic ideas floating around in the heads of the item writers. Maybe they sometimes decide to put something in again, or they're trying to reinforce a particular concept. We don't know what concept that is, and there's no guarantee. For example, one that appeared for a while was prime factorization of the year. And we haven't really seen that too much in my recollection in the last few years. Another one that was formerly pretty popular pre-2012 was leap year problems. And I haven't seen a leap year problem since around 2012 on the tests, but those were themes that carried for a few years, and you never know, they could come back for a reprisal. Add this to your small notebook. I'll see you in the example, and I'll also see you guys in the next video. All right, and I thought that I had already filmed a video and done Stewart's theorem in it. Little did I know, I looked through all of my videos for quite a while, did not find one. So you're going to get one. We're going to film one. I found one I wanted to do with this concept to demonstrate it. As usual, you don't have to use Stewart's theorem for this, but I think it's kind of nice. 2002 AMC 12B, problem number 23. In triangle ABC, we have AB is 1 and AC is 2. What can we do with that? I don't know. I'll probably start like, let's just go 1 like this and 2 over that way. About like that. We don't know what it looks like, right? Now, how do we know what point goes here? Well, A is on both of these. So I'm going to put A here and 1 here, not 1 here. AB is the 1 and then AC is the 2. Okay. Something like this. Okay. Side BC, so this is 1, this is 2. Side BC and the median from A. Well, where's the median from A? Well, the median from A goes to the midpoint. So I would find the midpoint maybe here or so. I'm going to connect that so I can draw a straight line. Woo! This would be the midpoint. I'm going to call it M or something. Those two things, side BC and AM, they have the same length. Now you can see this is actually a little bit shorter, it looks like, than AM. You just think about it conceptually, right? You're not going to have a perfectly accurate drawing. It wants us to find the length of BC. So BC is this whole length. I'm going to call this X and this X. I like to use X in those situations. So if BC is 2X and it has the same length as the median from A, so then this length right here is 2x. Okay? Now, we said we're going to try and use Stewart's theorem. What is the formula for that? Man plus dad equals BMB plus CNC. Okay, so, but we said again, don't just memorize the letters. Memorize how it plays out. And this is why, because it's not always called D. We called it 2x in this case. Okay? So let's think about the A part. The A part is here, plus I've got a point called M. That could get confusing. Remember that the M and the N are just the two pieces that the CVN creates. And any line from the vertex to the opposite side is a CVN, including a median, including an angle bisector, all of those things. Okay? So because of that, this is the CVN here, this is the M, this is the N, the A is the whole thing. So it's going to be X times 2X. That's going to be 2X cubed. Plus DAD, that's the 2X. This, don't forget, is 2X. So 2X times 2X, that's the A, back to the D is the 2X. Again, it's this whole thing back to this. Remember it conceptually, like the visualization of putting these together more than just this. It'll be much easier for you to recall it. And in case they move things around, like they called this side M or something, that can throw you off. That's why you don't want to rely just on letter memorization of formulas. Okay? So then what? 2x, 2x, 2x is going to be 8x cubed. Equals, we want BMB, again B is this side, 2 times X times 2. Usually we had B over here last time, it's fine though. 2 times X times 2, again the visual is more stronger than the letters, In the other one earlier, I think B was over here and C was over here. See, it gets confusing. So 2 times x times 2 is 4x, plus I'm going to go from here to here, back to here again. That's 1 times x times 1. It's just x. Right away, this is going to be 10x cubed equals 5x. We already know x is not 0. We can go ahead and simply divide by 5x because we know we're not dividing by 0 or a negative or anything like that to worry about anything weird happening. You're going to get 2x squared equals 1. Divide by 2 to get 1 over root 2, and that's what x squared equals. Oh, I'm sorry. X is going to equal. I should have written 2 first. I jumped ahead in my mind. So x squared equals 1 over 2 square root. You're going to get 1 over root 2. After that point, that's what x is equal. What about the negative? Doesn't matter, right? So 1 over root 2, but that's not the answer. We want to know what BC is. BC is 2x, so I want 2 over root 2. And a cool trick I like at the end of these kinds of problems, you can turn 2, it's root 2 times root 2, right? So I can just attach the root 2 here, put times root 2, and it's the same thing, so I cancel. I know it's only a couple seconds, but for me it's a little faster and it looks cool in my head. Just to me, not to anyone else. Anyhow, that's going to be it. It's going to be root 2, answer choice C. There is an example of how if you recognize the potential application of Stewart's theorem, you can quickly calculate what you're looking for. Again, why is it 2x and not just x? Because BC is this whole side, and we only had x. 2 over root 2 is root 2. Answer choice C. I hope this helps you guys gain one more tool in your tool belt, Stewart's theorem, and maybe it'll help you on this year's test, which we've got about 8 weeks to get to. You guys have a good one. See you in the next video.